is bridging the memory hotness gap in edge systems with hotness-segregated object allocation. And the talk will be given by Ruizhe Wang from Peking University.
Yes.
Please.
Okay. Thank you. Good afternoon, everyone. This is Ruizhe from the Peking University, and today I'm also delighted to present our work, bridging the memory hotness gap in the edge systems with hotness-segregated object allocation. This work focuses on bridging a subtle but costly mismatch in existing memory management subsystems. And this work is a collaboration between the Peking University and Huawei Technologies, and we are honored to share it at the conference. Yes, the edge systems often run with limited DRAM, so this makes memory one of the tightest resources in the real-world deployment. To use the memory more efficiently, the existing systems often use some hotness-aware approaches for optimization. Let me give you some example. The memory swapping will evict some code pages to the slow storage to reduce the memory pressure and keep the hot pages into the fast DRAM to achieve a better performance. And the memory deduplication prefers to share the code redundant pages to make more available memory and preserves the other hot huge pages untouched to keep the performance. So both of these two mechanisms are sensitive to the same issue. The kernel must exactly know which pages are really hot and which pages are really cold. If this page information is inaccurate, then both of these two systems will suffer from performance degradation. For example, if the memory swapping wrongly evict a page to the slow storage, and the application will suffer from the extra page faults because they need to bring the page back to the DRAM from the slow storage, and as well as the corresponding expensive I/O. If the memory deduplication wrongly shares the pages, and the system may incur additional overheads from the copy on write, or just losing the memory saving opportunities. However, the page hotness is not always accurate because the kernel observes the hotness as a page level granularity. But the memory objects in the same page can have very, very different access frequencies. So this is a page hotness skew, where the hot and cold objects are located in the same page at the same time. So this figure shows this pattern. The dark and light regions are interleaved in the same page instead of forming a purely hot or purely cold regions. And this makes the layout will confuse the page level classification because a page may look very, very hot even if it only contains only a few hot objects. As a result, in our micro benchmarks, these skewness can significantly degrade the memory access throughput by up to an order of magnitude. The root cause of the skewness comes from a mismatch between the system and the application, because the kernel managed memory by the page hotness, but the general purpose allocator will place objects according to their size classes. These two rules are optimized for different purposes. The kernel can only conduct page-level operations through the page table, so it wants a cleaner hotness signal to achieve the page-level operation. But the general-purpose allocator used by the allocation prefers to use a size-segregated placement strategy to achieve a faster allocation and reduce the memory fragmentation as well. This will create the mixed pages, because the same size objects with different hotness can be placed together in the same page. But the objects with similar hotness can be scattered across different pages because their size classes are totally different. After the allocator forms this layout, the kernel has limited operations. They can only scan the page, classify the page, split the huge page, or just evade the page to the slow storage. but they cannot change the page layout of the objects inside the page because it is already determined by the allocator instead of the kernel. So our insight to address this problem is that we need to place the objects with similar hotness together instead of according to their size classes. Therefore, we present a new memory allocator, hotmalloc, with the hotness-segregated allocation strategy. The hotmalloc will partition the entire heap memory into several subheaps, and each subheap will own the continuous virtual memory pages to store the objects from the one hotness class. And the object is allocated from the corresponding subheap that exactly matches its expected hotness. So with this layout, each page could become more hotness uniform. Therefore, this can reduce the page hotness skew and gives the kernel a cleaner signal for the future memory optimizations. The key challenge behind the hotmalloc is that we need this hotness information before the allocation time, that is, before the object is actually allocated and used. And we don't expect to incur too much runtime overhead. Therefore, hotmalloc uses a profile-guided optimization-based method. It will profile from the previous runs and learns the relation between the allocation as well as the corresponding hotness. And then it will use this historical information to guide the further allocation. So there are three key components in hotmalloc. The offline analytics will learn which allocation context creates hot or cold objects, and synthesize an application-specific allocator with the hotness information inside the allocator. And during the runtime, the synthesized allocator will identify the object hotness according to their allocation context, and will allocate memory from the corresponding subheap to achieve the hotness segregation. And finally, the allocator could expose the subheap hotness directly to the kernel through our interface. So the kernel can directly use this exposed hotness information instead of just relying on some online monitoring. And this way, we could leave the expensive profiling to the could leave the expensive learning to the offline and just leave the only lightweight classification as the allocation time. During the offline phase, the hotmalloc uses profiling to collect the allocation and access information. The profile will instrument one run and tell us which allocation creates which objects and how often of each object is accessed. Then it will map the allocation context to their corresponding hotness classes. And after this analysis, the hotmalloc will generate an application-specific allocator for the deployment usage. The key point is that the profiling cost is paid before the real-world deployment. And during the normal execution, the hotmalloc does not need any online page sampling, and it also avoids the read and write barriers on the memory accesses. The learned hotness will becomes a deployment artifact for the hotness estimation instead of a runtime text. And during the runtime, the hotmalloc needs to identify the page object hotness according to the allocation context. The whole process is simple and efficient. The hotmalloc uses the calling stack frame to represent the allocation context. Yes, the calling stack frame will be encoded to generate an object ID, and the hotmalloc will use this ID to find the target subheap. And finally, after this identification, the hotmalloc will allocate memory from that subheap to achieve the allocation. We can find that the placement decision only happens once when the object is created. And after the placement, the object can be used normally. There is no relocation and no per-access monitoring overhead. This keeps the common memory access paths unchanged and therefore leaves the hot malloc transparent to any applications. Based on this Hotness-Segregated layout, the hot malloc also provides two simplified memory management strategies for two specific scenarios. That is for the swapping and deduplication. For swapping, our goal is that we need to protect the most frequently accessed objects. So we use the hot first strategy, which groups the hottest objects into one hottest subheap, so that these pages in the hottest subheap can be more likely to stay in the DRAM even under the memory pressure. And for the deduplication, the goal is totally different because we want to find some pages that can be safely shared with low performance risk from the unnecessary and additional command write. So we use a code first strategy, which groups the coldest objects into the coldest subheap, so that the system can just only focus on these cold pages for sharing. And other pages in the hot subheap can keep untouched to achieve a better performance. Beyond this, the allocator could also provide a simple interface to expose the subheap hotness to the kernel. For example, for each subheap between the ADDR and the ADDR plus dice, the hot malloc could expose the hotness to the kernel through our newly added system call interface. This is highly useful because the allocator knows more about the object hotness distribution than the kernel, so that the kernel can cheaply directly use this information instead of just relying on some online monitoring by itself. Okay, for the evaluation, we test both memory swapping and deduplication, these two scenarios. And we compare the hot malloc against the common legacy allocators such as the one from glibc, jemalloc, and memalloc. And we will also compare the hot malloc with other hotness-aware approaches, such as memory teas from SOSP, store from the yesteryear OSDI, as well for the deduplication scenario. We also compare with the SmartMD Plus that are published in TOC. Our evaluation question is very direct. We want to know if we improve the page layout, can the kernel mechanisms actually become more effective? Okay. The first result, we first checked whether the hot malloc could reduce the page hotness crew. And then in our macro benchmark, the hot malloc could reorganize the memory so that the huge page become much closer to purely hot or purely cold regions. And as a consequence, it can improve the memory access throughput by up to 7.6 times. And for the real-world applications, we also measure the maximum within page hotness gap. That is, the different access of the most frequently accessed objects and the least frequently accessed objects in the same page. And this difference are dropped by 8 to 25 times. These results confirm that the hot malloc changes the distribution of the hot and cold objects in the memory. And as a result, the page level hotness becomes more cleaner, and so that the kernel can rely on this cleaner hotness signal for better optimization. Under the memory swapping, we found that the hot malloc improves the overall performance by up to 42.1%. The main reason of this improvement is the fewer page faults. We found that the hot malloc could reduce the page faults by up to 90%. This happens because the hot objects are grouped together in the same huge pages, and under memory pressure, the kernel can keep these pages resident and just evade other colder pages more accurately. In other words, we can more accurately evict pages, and then we therefore could reduce the unnecessary page faults. The hot malloc could also help preserve the huge page. In Linux, we found that the swapping can inevitably involve the huge page splitting, because when hot and cold objects are placed together in the same huge page, the kernel must split the entire huge page into several 4 kilobit small pages, and just evade these pages that contain the cold objects to the slow storage. And this splitting will lose the TRB benefits, and as well as incurs other additional overheads such as the TRB shutdown. Hot malloc groups some hot objects together, so it makes the huge page more stable during the execution. And as a result, the hot malloc could keeps an average huge page ratio of about 93%. The same layout principle also helps the memory deduplication. With the code-first strategy, the hot malloc could group the code object together, and therefore the system can just focus on these code regions for sharing, while other huge pages can be preserved for performance. On the contrary, SmartID Plus use some online monitoring according to the access speed from the page table. So they need this mechanism to determine the page hotness as well as which pages to share. However, this page level classification may be misleading because of the page hotness crew, and therefore the system will lose some memory saving opportunities. Compared to this, by giving a more cleaner page hotness, the hot malloc could deduplicate up to 40.6 times more memory, while keeps the memory performance gap stay below 3%. Okay, let me conclude. The page hotness crew comes from a mismatch between the object placement and the page level kernel management. The hot malloc reduces this crewness by placing objects with a similar hotness together. It uses the offline profiling and the lightweight allocation time classification, as well as the simple kernel-facing interface to expose the heap hotness. And with this layout, the swapping could become more accurate, and the deduplication could save more memory. Sometimes the best system optimization is not always a more complicated policy, but could be a better interface between the different layers. So we have found that a better memory policy could start with the better memory layout. So this is the end of my presentation, and thank you for your time. And I'm happy to take your questions.
Thank you.
Thank you for the great talk. I was very interested in this research project. I'm wondering about the experimental setting, by the way. So you mentioned you evaluate your scheme with the MEMTIS and SOAR. Those two papers were for, from my understanding, those are for CXL memory. So do you assume this scheme may work for the embedded systems as well, or what is your evaluation setting?
Yes, we conduct our evaluation in the server. Yes, but we think our design is not platform specific. We target for the resource limited scenario, so it will also, at least it will also work in x86 platform. And at least for some other ARM platform, I think it may be work also, but I do not try it yet.
Hi. So if I understand correctly, you have one subheap for the hot objects and one subheap for the cold objects, right?
Yes.
So but like, of course, in practice, objects are not just hot or cold like binary. There's kind of a continuum, right? There's kind of a spectrum, right? So how do you decide where to draw the line, like this object is hot or this object is cold? To distinguish?
Sorry, I didn't get you.
What makes an object hot? Like, what is the...
Like
What's the criteria to classify them?
Or like, here's a concrete example. So you look at the profile information from the last run and you say, okay, this object was accessed 100 times. Is it hot or is it cold?
Sorry?
Sorry, maybe am I talking too quickly?
Yes.
Sorry. So for you're using profile guided optimization, right?
Yes.
So the previous run, I assume you're seeing, okay, this object was accessed 100 times as an example.
Yes.
Right? So this object that was accessed 100 times, is it hot or is it cold?
Yes, we classify the hot objects and cold objects not according to its absolute access frequencies, but we will order the entire objects and find the top K objects as the hottest.
I see, and how do you choose the value of K?
Sorry.
Sorry. How do you, so you choose the top K objects are
Yes.
hot.
Yes.
What's the value of K?
This K could be determined by the administrator. This is
Okay,
user defined.
So it's configurable. It's configurable. You can choose what the value is.
Actually, it can be determined by the volume of the DRAM. So you need to keep the top K, the hottest object, into DRAM. Therefore, the DRAM volume could keep these objects in the memory. So we can determine the K according to these objects, the size of these objects, and find the corresponding K.
Okay, that makes sense. Thanks.
Oh, thank you.
Have you noticed some objects, if they might be cold in one part of the execution and hot in another part of the execution?
Execution.
There could be objects that start off cold, but later become hot, or vice versa.
Okay. We do not. We target for the object hotness across the entire lifetime instead of some windows within some window. Yes, we need to place some hot objects together, and to create to provide a cleaner hotness signal. So in case there actually maybe some objects maybe become cold after some time. Yes, but during the entire lifetime, it is actually hot if it is really hot. But it actually become colder at some time. But we focus on the entire lifetime. Yes.
One quick one. Maybe I missed this. This is for DRAM, right?
We do not have specific swapping method. The DRAM could also work.
All right. So I was wondering, did you notice any degradation in terms of parallelism? Like, for instance, if you pack the DRAM pages, then you would get many bank conflicts, right? So whereas if you have hot accesses across banks, then you would have more parallelism within the memory subsystem.
Yes.
Is that something that you noticed? Because you are packing the hot objects in a page, so you will reduce the amount of parallelism.
No, we need to prioritize packing other code objects. Therefore, this should be a co-design between the system and the application.
So as an example, right?
Yes.
If everything goes into one page because that's the hottest,
Yes.
then every access will result in a bank conflict in DRAM.
These objects will be put in the DRAM and will not be compact.
Right.